this subject has this subject has nothing to do with all the exotic and cool things that are going on at the frontier of physics. And that's matter physics, like fractons and topological phases and all the classification and all the algebraic things that people are doing. So I'm even surprised it was noticed by more than a handful of colleagues who used to work on this kind of stuff. But anyway, so here I am. So I'll tell you about this work on this new state of vortex glass, and that it's on the archive recently. And so, with the tutorial, to put things in perspective, it'll give me a chance to kind of, give you some background. And most of this background, may shock some of the younger members of the audience, that there was actually physics done since the discovery of quantum mechanics and discovery of topological phases and study of topological phases. So yeah, we used to do, even before topological phases, we used to do physics, and it was pretty exciting. And some of it is what I'm going to talk about. So I'm going to, as suggested, I'm going to break it up into a tutorial to vortex physics in type 2 superconductors, and then I will launch in and talk about Smectic vortex glass. So let me start out then with basically textbook kind of material that hopefully everybody's familiar with, but just to get everybody on the same page. There are two types of superconductors, type 1 and type 2. The focus will be on type 2 superconductors, which is most alloy superconductors are actually type 2. And in fact, these are more plentiful in nature. And they're characterized by superconductors are characterized by two length scales, which one length scale is lambda. Lambda penetration length describes the stiffness of the electromagnetic field or electrostatic magnetic field or the gauge potential. And the other scale is the correlation length or coherence length, describes the stiffness of the superconducting order parameter. And when you're in a regime where the magnetic fields are far stiffer to non-uniform distortion than the order parameter, then you're in this type 2 regime. And this is the regime in which, when you start out with a Meissner effect in the superconducting state below TC here, and you apply a magnetic field, rather than what happens in type 1 superconductors, where you immediately, via first order transition, destroy the superconducting state and jump to a normal state. Here, instead, there's a intermediate abrikosov vortex lattice state discovered by Abrikosov in 1957, where vortices do penetrate, but they penetrate in terms of these filaments or circulating currents, with exhibiting these two length scales, C and lambda. And and so that the two critical fields, HC1, HC2, is the lower one is the flux quanta per London penetration length squared, give or take, and HC2 physically is the scale of the applied field, a scale of actually flux density when vortices begin to overlap. So then the flux density is one flux quanta per coherence area. Okay, but so, this was the picture that existed since 1957. But when the high temperature superconductors were discovered in the late 80s, the field of condensed matter physics somewhat splintered in that, part of the community focused on the mechanism and the microscopics of these newly discovered cuprates, and the other half, of some fraction, maybe smaller than half, focused on the magnetic field phase diagram that I illustrated here, and how it's different in these newly discovered superconductors. And there's something really, so there was a long period of study of these magnetic field temperature phase diagram, and lots of progress has been made, and that's what the introduction is about, or the tutorial is about. So the first thing that happens is, because of the properties of high temperature superconductors, first they're layered. Second, they're high temperature, so they occur at high temperature. And thirdly, the coherence length is very short. As a result, these vortices that are treated in mean field theory by Abrikosov kind of become dynamical entities of their own. They take on a life of their own. And just like any other, constituent, you could have a crystal phase of it, or you can have phases now. You can start talking about phases of this vortex matter. And Abrikosov lattice is just one phase. It's the solid phase of these flux filaments, of vortex filaments. But of course, like any lattice, one can imagine melting that lattice into what would be then called a vortex liquid, as was in the context of high temperature superconductor, was suggested by Nelson and explored extensively by Nelson and followed up by many, many people. But in actually the original work of Eilenberger already makes a note, and then Daniel Fisher in the other context, in the 2D context, already points out that the possibility of this vortex liquid phase. And really, in principle, this phase is always there. It's just really, you can think of it as a theorist just going beyond mean field theory. And it's qualitatively, it's indistinguishable from a normal state. It's just a crossover here. So in this simple, clean sample, this is just a first order transition from a crystal to a liquid. And while the original HC2 line is just a mean field line, mean field crossover line from a vortex liquid, where the vortices or fluctuations of the superconductivity order parameter are non-linearly realized, are in a nonlinear regime, so you can then identify vortices. And beyond this, the vortices are overlapping, so you would call that a normal state. And there's a nice, typically fairly sharp crossover across this mean field line, but qualitatively, this vortex liquid is indistinguishable. Qualitatively, it's indistinguishable from the normal state. In terms of resistivity, and there are many other phenomena that follow from this enrichment of the phase diagram. The behavior is quite striking. In zero field, you have a nice sharp phase transition at the critical temperature, let's say here, 80 Kelvin. But when you put on a magnetic field, critical temperature, the actual place where resistivity actually vanishes is far lower. And there's this large intermediate region that's magnetic field dependent, that where the resistivity is non-zero, though there's a precipitous drop in it compared to the normal state value, and that's associated with this vortex liquid state. By the way, please feel free to interrupt me. I'd rather this be a dialogue rather than a soliloquy. So that's the point of the tutorial. So interrupt me at any point, and I hope Arpi can keep track of questions just in case I don't notice them in the chat.
Yes. Yeah, if anyone has questions, I think you can people be just free to interrupt, right? So,
right. Yeah. Feel free to interrupt me. And there's a lot of experimental data that actually sees that there's this first order transition, and most beautiful latest data was by Eli Zeldoff that actually showed thermodynamically that there's a first order transition across this melting line. So now this is the actual transition. It's a first order melting line, at least in the absence of disorder. But then building up in complexity, one can move on to more realistic situation. And that's when these vortex phases are subjected to disorder, as any respectable condensed matter solid state system is. So, you have all kinds of vacancies and interstitials of, in just actual atomic structure. And you could also irradiate with electrons to create more impurities. And it's actually quite crucial for applications. And it's interesting from intellectual point of view to explore how even at zero temperature or low temperatures, you have this elastic medium, namely a vortex lattice, how it responds to a random pinning potential, which is how we think of these impurities or these green point disorder, indicated in green circles. This has a long history, actually predating high temperature superconductors. But this sort of experienced a renaissance with high temperature superconductors, where now previous phase diagram that I showed, in the absence of disorder, it still has a vortex liquid. There's still a normal regime, a vortex liquid regime, but there's still a Meissner state. But then the vortex crystal has been converted to what we call a vortex glass. I mean, one at some point could say there's a question mark here whether a vortex glass actually exists. Is it as a separate state of matter? But the upshot is that in 3 dimensions, we expect that it does exist in the presence of pinning disorder. And one way to analyze this, the stability of a crystal phase 2-point disorder is to do a Larkin analysis. And so Larkin analysis simply estimates, it's a criteria rather than a crossover. It estimates, it considers the distortions due to the point disorder, due to the random potential of this of a perfect vortex lattice, and asks whether those distortions build up, let's say in 3 dimensions, for any infinitesimal or weak amount of disorder. And can they build up so much that the distortions, namely mean square fluctuations, become, or root mean square fluctuations become of order lattice constant A. And when they become of order lattice constant A, then one can say that now the vortex crystal phase has been undergone an instability to a vortex glass state, or a state at least that it's not, doesn't break translational symmetry. It's no longer periodic. Well, in fact, when you do this calculation for the simplest description and more elaborate descriptions, you discover that this thing in 3 dimensions, this RMS fluctuations due to disorder, even at 0 temperature, diverge with system size. And so because of that, that means you can get to a system length, which we call Larkin length. And that length is finite if you're below 4 dimensions for point disorder. That beyond this length, below this length scale, the system looks ordered and looks like crystalline, but beyond this length scale, it crosses over to its asymptotic state, which is doesn't break translational symmetry. And of course, this is just a suggestion that, or a hint that there's a new phase that may emerge. It's not a proof that there's a glass state. One then has to study the physics beyond this Larkin length. But this Larkin length immediately at least tells you the fact that it's finite in the strength of disorder. So when the disorder is weak, the fact that this length is finite tells you that the crystal is unstable in 3 dimensions. And notice it goes inversely proportional to the disorder strength or pinning potential. And so, of course, this length is diverging as the pinning potential is dialed down to 0. And then ultimately, then you get back to the crystal phase when the pinning potential goes to 0. So
the phase diagram that you have is above a certain disordered strength?
No, that's the thing. For arbitrary weak disorder, because this thing diverges with system size for arbitrary weak disorder,
okay,
in 3 dimensions, and the upper critical, or I could call it lower critical dimensions 4, it's just a instability of XY model in the random field. That's really what it comes down to in terms of a calculation, with only some bells and whistles to account for vortex physics. But this, it's really just a random field XY model in 3 dimensions or below 4 dimensions. Because this thing diverges with length scale, that means no matter how weak your disorder is, for arbitrarily weak disorder, there will always be a length scale beyond which this criteria will be satisfied. And therefore, there's always a vortex glass state that replaces the crystal.
Okay, thanks for clarifying.
And that vortex glass state can undergo a first order transition to a vortex liquid, or at least experimentally, and also the theoretical arguments that at high temperature or high field, it undergoes a second order transition to a melting transition of the vortex glass. And in fact, this is what I indicated here. Here's some data. So here's the tricritical point. Here's the first order transition. And here, what's seen by the SAFAR data is actually a continuous, what seems to be a continuous transition. Okay,
Well,
But
what's the behavior of the resistivity drop? Like, can you quantify that using this theory?
yeah, so I will touch on that in a couple of slides.
Okay, thanks.
Okay, but suffice it to say, already here I'll say that part of the reason, at least a practical reason of interest in glass, is that this elastic medium is now pinned as a glass, goes into a glass state, and the key observation by Fisher, and Hughes in the early 90s is that this is really a superconducting state, in contrast to a vortex liquid. It really has an Edwards-Anderson-like order parameter for superconducting order parameter, made up of a superconducting order parameter. So I even though this is somewhat of a, for completeness, well, okay, so you can image these vortices, and you can see here that in addition to like local regions of crystallinity of triangular lattice, you have all kinds of imperfections in your lattice, some vacancies in interstitials, lots of dislocations, grain boundaries, etc. So that's really how one can think about, at least, intermediate or strong disorder limit is some kind of a structure like this, where you have a pin medium. At short scales, it's crystalline, but at long scales, it's fully disordered, has dislocations, and has vacancies, interstitials, and grain boundaries. And these actual images, this is what's called the bitter decoration image of vortices. And here's the squid image of vortices. Here it's far more disordered because this is in the film. So on one hand, one is interested in vortex matter, but in fact, I can't resist but to mention, and I'll continue on that sort of digression more, is that although this was all inspired by vortex physics, in fact, it's connected to a much bigger subject of pinned elastic media, which can occur in charge density waves, random field XY models, liquid crystals confined in aerogel or other porous media. What else? Friction and various other kind of a phenomena where you have some kind of a Goldstone mode theory. You're in the ordered phase, and then you subject it to a random potential. So the physics here, which is displayed here for vortices, is actually much broader type of physics. It's a physics of competition, low temperature competition or zero temperature competition between elasticity and random potential. Okay, and that's kind of a subject of glasses, if you think about it, except I call it a baby glass because in this context, unlike structural glass, the disorder is actually imposed by hand by external random potential rather than structural glasses where it's self-generated. I also, have hard time resisting, but to mention that and this will come back when I talk about Smectic glass, the subject of the seminar, is, a real question of principle arose. And this was really first brought to everybody's attention, explored extensively by Giamarchi and Lassalle, and that is the existence of so-called Bragg glass, which one can think of as a topologically ordered glass of vortices, or more generally, random field XY model, where there are no topological defects. In the context of vortices, it's no dislocations. So the question of principle is, if the disorder is sufficiently weak, is it possible to have a randomly pinned elastic medium or a randomly pinned vortex lattice that forms a glass, but that glass is topologically ordered in the sense of that, although it's distorted elastically, it's ordered topologically, namely has no dislocations. In the same vein, then, one thinks about Castello-Stalos phase as a phase that is disordered elastically in the sense of a Goldstone modes, has power law correlations, but or logarithmic correlations in the phase field or displacements, but does not allow individual vortices. So this is sort of the disorder analog of that. And so one picture one may have is that at low disorder, you have actual Bragg glass phase that's stable, which has no dislocations. But then when you increase disorder, and you can study its properties, as was done by Gianmarco Lidusal and many other people. But then when you increase disorder beyond some threshold, it undergoes this Bragg glass driven by disorder, undergoes a phase transition to a vortex glass, which has now proliferation of dislocations. And the current status of that question is that in 2 dimensions, this does not happen. There's no Bragg glass in 2 dimensions, but in 3 dimensions, there are strong arguments, particularly due to Daniel Fisher using real space RG, but also by a variety of other authors, and many I don't even list here, that argue that Bragg glass is stable in 3 dimensions. One cool property of Bragg glass, well, okay, so there are, sort of 2 points of view. One can say, well, there's this question of principle, does Bragg glass exist or not? But alternatively, one can just think about, even if Bragg glass does not exist as a distinct phase from a vortex glass, and there's a finite Larkin scale, there's a finite scale, dislocation length scale, which is not infinite. If you have such a situation, that means dislocations really beyond this length scale unbind. However, one can always look at a smaller system sizes and then study the system on the smaller scales. And when one does that, one discovers that, in fact, you can do a very detailed analysis, and the correlations of the displacement actually display a log below 4 dimensions, display a log divergent correlations with a prefactor that's universal. So unlike the Kostelos-Tallis phase driven by thermal fluctuations in 2 dimensions, this phase, this system, and that only happens in 2 dimensions, this is analogous, except this behavior persists between 2 and 4 dimensions. So in particular applies to 3 dimensions, and the prefactor is actually a universal number, unlike the Kostelos-Tallis transition. It's just a number, pure number. So there are many other consequences of this. Now let me just touch on some of them. So, what is the, once you have elastic medium that's pinned, and one can think about friction, for example, or, earthquakes and other examples, but in particular, we're talking about vortices. There's really 2 paradigms. There's a vortex glass picture of Anderson and Kim, where you have independent particles sitting in the random potential. These are the vortices. And when you try to push on them, they can move. And of course, since the barriers are finite, if they move individually, then there's always a Arrhenius activation. And so even though the resistance is small for their motion, that's induced by their motion, it's exponentially small, but it's finite. And therefore, strictly speaking, in this picture, according to Anderson and Kim, which is ancient now, I think goes back to 70s, there's really as soon as you have vortices, there's no superconductivity, because there's really linear resistivity is finite at all fields and all temperatures, no matter how low. On the other hand, a complementary picture, which is the collective picture, which is what we believe actually happens if you have a vortex glass state, which we believe exists, is that you have elastic medium and it's pinned. And when you try to move it by applying a current, it moves in the perpendicular direction via, let's say, Magnus force or Lorentz force. Then collective regions move, collectively over random potential. Here's a cartoon of it. And as a result, this pinned elastic medium can creep along, but because it does it collectively below the glass transition, it actually does it. It can always move non-linearly, but there's really, it has an IV characteristic that is strictly non-linear, namely has no linear response coefficient, and therefore resistivity is actually 0, strictly speaking 0 at low temperatures and a low current. So this thing is strictly nonlinear. Of course, at large currents, it crosses over at fine 85 temperature to a flux flow resistivity where it does have linear normal state like IV characteristics. Okay, and this has been explored extensively, that's creep behavior. And this is what we believe the actual picture is. So this is just contrasting mean field independent picture versus the collective picture in transport. And there's all kinds of other stuff that maybe I'm looking at the clock, so maybe I'll skip over this. Well, okay, I'll just mention that once you start thinking about this moving elastic medium, pinned but creeping or maybe fast moving elastic medium, there's all kinds of things you can entertain. In particular, one can imagine, and in fact, this was observed in numerics, and we studied this with Liam Balent and Christina Marchetti in '97, but a problem that first was posed by, well, a variety of people, namely what happens to the Bragg glass or vortex glass, which shows 6 peaks, which may be broadened by disorder. These are reciprocal lattice peaks, Lorentzian-like peaks. What happens to them when this Bragg glass or vortex glass starts moving at high velocities? And what we predicted, and in fact was observed numerically, is that it transitions to what we call a transverse Smectic state, where you get layered structure, where there's still some periodicity in the direction transverse to the direction of motion, but there's no periodicity in the direction along the direction of motion. And as a result, you can see here the structure function, you get 2 Bragg peaks rather than 6 Bragg peaks at low velocity. So at low velocity, you have 6 Bragg peaks, but at high velocities, you get 2 Bragg peaks. Namely, you've transitioned to this transverse Smectic, and the whole picture sort of is, in a cartoon way, is given in this phase diagram. This is now non-equilibrium phase diagram for moving elastic medium that we use to understand vortices and other states of matter. Are there any questions?
Sorry, could you say more about the periodicity along the transverse direction?
Well, it's an observation. You can think of it as an observation that, you start out with a state that's, has periodicity, at least short range periodicity in all directions. So it forms a triangular lattice, or, it forms a state like this, which is distorted by disorder, but it still has short range periodicity in all directions. But then when you begin to move this medium, what we predict is that and so that describes by 6 peaks. But when you begin to move this medium, it goes from a vortex slick, it melts, but then it reforms into something that still maintains periodicity in a transverse direction, but no periodicity in the direction of motion. And that's the transverse Smectic and indicated by these 2 Bragg peaks.
I see. Okay.
Okay, so this is just sort of so to finally finish the sort of the overview and all the ingredients that I will need to discuss in the seminar, let me talk about one more glass state, so-called Bose glass state, or you can think of it as an anisotropic vortex glass state. And this was introduced by Matthew Fisher and also Nelson and Vinokur, and studied extensively, particularly by Nelson and Vinokur. And the idea is that in addition to point disorder that I discussed, you have vortices and you have point disorder. There's also correlated disorder in the system, namely screw dislocations, all kinds of, twin planes and all kinds of correlated random disorder. And so I indicate here columns. But in addition, for practical reasons, why want to increase pinning of vortices to improve its superconducting properties. So what people just decided to do, and in fact, it worked incredibly well, is to irradiate a sample with using heavy ions and thereby create tracks or columns that are randomly positioned, but they're correlated in the z direction. And now, as indicated here in this cartoon, vortices are sitting, prefer to sit on these columnar defects. By the way, and this is something I'll return to, and this was made use of by Nelson and Vinokur as an analogy, and also of course, discussed by Matthew Fisher. If you think of the z direction as time, one can think of this as the space-time picture of bosons in the random potential, where this is point disorder in the random potential, where this is time. And that's, of course, a famous problem of Bose glass. And that's why Nelson and Vinocourt gave this state a name of Bose glass, but in the context of vortices. So here's another reincarnation, another view of this. So there's a phase diagram, beat versus temperature phase diagram. But let me focus on one aspect of Bose glass that's quite special, namely what happens as a function of temperature. So let's go along this axis through Bose glass. Here's the temperature axis. What happens if you apply a transverse field? Namely, you try to tilt the magnetic field relative to the columns. You try to apply the columns at some angle, or you try to apply an external field at some angle. And what they discovered is, not surprisingly, if you understand Bose glasses in quantum context, that the state is actually stable up to a critical value of the tilt angle or transverse field to this tilting. And so they call this a transverse Meissner effect. Namely, Bose glass phase excludes transverse field or tilting of the field. And that's easy to understand qualitatively. Simply, vortices are stuck on these columnar defects. And so when you try to tilt them, they resist, and they resist in a qualitative way. And as a result, to go, to really depin them and tear them away and to destroy this phase at low temperatures, you need to apply a critical value of the field. So this is like the HC1 for the transverse field, okay, or the tilting angle. So, okay, so with this background, I'm going to stop and before I, and we can take a break before I launch into the Smectic Vortex class and the related stuff.
Actually, Leo, could you remind me, why did the magnetic lines have to be vertical?
Well, I
Why does the
apply an
system work
external
that?
field. I apply an external field in this direction.
But then you add a tilted field.
But then I try to tilt it, so I apply a field in this direction. But that doesn't mean that the flux lines will follow that field. They might still want to prefer to follow the columns because they're pinned by the columns. Think of columns as holes in a superconductor. When you have holes, then vortex line is also in a sense a hole in the superconducting order parameter. So you lower your energy if you continue following the columnar defects, the normal tracks, rather than tilting away. So, there's a possibility of doing this, or there's a possibility of following the columnar defect and then hopping to another columnar defect. And this is something I will discuss.
Oh, okay, I see. Thanks.
Okay.
Yeah, am I remembering correctly? It's like a cosine, like the cost is like cosine of the relative angle, something like this, like H dot M.
Exactly. You're trying to, yeah, exactly. You're just trying to, you picked out an axis, and so the vortices like to run along this axis, but your external field doesn't have to be along that axis. It's very much like sort of a picture now in transverse direction, replaying the Meissner state. You can think of this as a Meissner state for transverse field, and this is the vortex state for well, I put question marks here, and that's actually the subject of that got me into the subject of today's talk, and then in the paper that I put out is what happens beyond this. It was sort of tacitly assumed that you basically get a crystal or maybe a vortex liquid once you depin. And so the question is what actually happens, and this is what's the subject of the next part of the talk.
Analog quantum language, if this.
I can't quite hear.
What is the analog in the language where it's a path integral of a quantum Bose system?
I think that's like imposing a current, or maybe imposing a canonically conjugate variable to current, like minus VJ.
And there's the non-Hermitian description of this.
Exactly.
Oh, I
Yeah.
see.
So, you know,
Which is like hopping to the right is bigger than hopping to the left
exactly.
in imaginary time.
Okay, thank you.
So this is sort of, you know, if you didn't follow everything, hopefully, you know, you can look back at the slides, but, you know, this is 30 plus years of, and maybe more, predating high TCs of sort of information. I sort of core dumped on you, sort of including the main ingredients that kind of pillars of the subject.
I'm going to use the break in order to overcome my strong sense of deja vu.
Okay, well, that's why I said it's a, you know, trip down
This is not
memory.
criticism. This is a reflection on, you know, on our education.
Right. Yeah. Well, that's what my opening remarks were echoing that. It also is echoing how old I feel giving the stuff. But anyway.
Hi, Leo. So could you go back to this plot where you had this moving liquid and moving smectic?
Here, sure.
So here F is what again? It's some force that you're applying.
Yeah. So, you know, I'm interested in vortices. So then here I put it, there's some effective F. If you would try to discuss a general, this is disorder and this is external, that's the force. Or you can think of it synonymously with velocity.
Okay, so is it at low velocities that you're saying you have like full sort of like bigger symmetry because you have a liquid while you keep reducing it as you?
Well, it's sort of like this. So this is kind of questionable. We don't know how to deal with this. We only understand it at high force or high velocity. The first observation is everything I talked about up to this slide, up to dynamics. Here's the Bragg glass or vortex glass. Well, here's the Bragg glass. Here's the vortex glass. Here's the phase transition right on this equilibrium line. Okay, F equals 0.
Mhm.
Then, you know, what happens when you begin to try to depin it? We know its effects of disorder are very strong, so it really reshuffles. But then the idea is that very large drive, you kind of average over disorder, so you get back to crystalline state. That's at large velocity. But at the intermediate velocity, something that we can control by perturbing around the state, and we can show that it's actually a state which has periodicity only in a direction perpendicular to the velocity.
But then when you have a moving liquid, somehow you have a lot more symmetry than moving?
Yeah, so you have more symmetry because you think of it like you're creeping along through a random potential. So you're tearing the hell out of, at any finite temperature, you're tearing apart this poor crystal that's pinned by impurities by forcing it to go through all kinds of impurities and imperfections. So then you destroy the crystal, and then at any finite temperature, it's really a liquid.
Okay, great, thanks. Okay. So if there are any more questions, I guess you can ask, but should we just restart in 5 minutes?
Yeah, I have to confess, I have an appointment after
Okay.
this.
Yeah.
So if the shorter is better, but
Yeah, so I think we have had a small break. So if you think we
no,
can
that's
go
just
ahead.
a couple
Yeah.
of minutes. It's fine. I'm happy, and I can also stick around and answer questions. I don't need to.
Yeah, so feel free to start whenever you would like to.
Okay, but maybe just for definiteness, let's just say I don't know, 7:47 or something. You know.
Yeah, sounds good. Sounds good.
It's a very nice intro, Leo. Thank you.
Okay, thanks.
That's what I should have said. It makes me feel back at home at Harvard.
Oh, I see. Right. Exactly. Yeah, and I get a fuzzy feeling in my stomach as well when I think about the subject.
I remember back, when I tried to, one time I had to give a presentation of this as a final project, a final presentation on some course in grad school. It was really hard to make sense of all the phases because there were papers at the time, in like early 2000s about Vortex slash and Vortex, etc.
Well, yeah, okay,
And
that's true.
so what phases exist in the end for sure? So
Well,
post glass,
I would say
I
would
guess
say that,
black glass, Vortex
the-
glass, yeah.
this phenomena of states of matter proliferation has its counterpart, but in spades, exponentially larger in high TC microscopics, of course, right? So
Yeah.
every mean field and every there's so many phases predicted, and if you haven't followed it from if you haven't followed it, it's not easy to distinguish those that are phases that are sort of how rigorous of a footing the phases are. So I kind of gave you things that the overview of those things that are real, that for the most part people would agree with, and the proliferation of phases is often due to the confusion by the authors or experimentalists, where they confuse a distinct phase from a crossover.
Right.
Once
that's
you
the
do
feeling I had.
crossovers, there's all kinds of phenomena that.
And you can organize it by kind of crystal order, right?
That's right.
Yeah, you have a crystal order, you don't have a crystal order, no motion, or you have some logarithmic crystal order, like parallel decaying correlations.
That's right. Well, that's sort of the basic picture. But then you start putting in anisotropy, you start putting in, moving phases, you start putting in, tilting
Point
phases,
disorder,
yeah, all kinds of other stuff.
Right. Thanks.
Yeah. So I don't know if people don't mind, maybe I'll start.
Yes, please go ahead.
Okay, so now I want to talk about Smectic vortex glass. And again, so here's the summary slide of all the slides that I've given so far. And the main thing that kind of motivated me to think about this is what happens outside of this Bose glass phase in the presence of tilting. And that's a fairly rich, actually, story, and that's what I want to tell you about. In fact, it was amazingly, as I was thinking about this, there were experiments in early 2000 by Henry Kieger in Chicago and Tom Rosenbaum in Chicago at that time. Your illustrious president now, Tom, who studied exactly this question along with many other people. But what they did unique is they studied both AC susceptibility, namely how superconducting the state is, how pinned the matter is. And they also had a Hall probe here to measure a response to the tilted field. So you see the field is along this direction, but then you tilt it and you ask whether vortices, and this is kind of answer to maybe picture answer to Kevin's question. So, some vortices, so they want to detect how much vortices depend from these columnar defects, basically. And they could do it simultaneously. And what they discovered is, in fact, that this phase boundary, this is the Bose glass phase. And this is the phase boundary of where describing the transverse Meissner effect. This is my question marks, what happens afterwards. But inside this phase, there still seems to be lots of diamagnetism. And so the system looks superconducting here, even though it's already been torn away from columnar defects. And the actual transition to the normal state or vortex liquid state happens here. And so then I wanted to ask a simple question. What happens as you tear vortices away from columnar defects in 3 dimensions with many columnar defects as indicated in this picture? But what I realized is I don't even know how to answer the simplest question. Suppose I have 1 columnar defect with many interacting vortex lines in 2 dimensions, or what I'll call 1 + 1 dimension. So you can think of this as time, if it helps you, and this is space. So how do you go from here to here? You're imposing this so far away, it has to be this. But how do you go from this one flux line that's pinned on here, and then you move away? As you move away in the x direction from the columnar defect, you somehow tilt. So amazingly, this is a rich problem, sort of applied physics problem. So here's the formulation of it. The Hamiltonian is just, you have elasticity in the x direction, elasticity in the z direction, and you have a pinning potential due to one pin. But now you imply an external field that external field that's tilted and tries to tilt flux lines or vortices. So now there's a competition. This term would like to tilt it and to follow the field, but the pinning potential due to columnar defect would like to keep it straight. So if you actually put in a pinning potential that sits only at the origin, you get this kind of a Hamiltonian. And those of you who have studied the Ladinger liquids and Kane-Fisher problem will appreciate that this is like a Kane-Fisher problem where there's a single impurity at the origin, where Z is time, and this is like the Ladinger liquid Lagrangian. But it's in the presence of external velocity, opposed velocity, that tries to make the system flow. But in this case, it's just much simpler. It's just tilting. Let me just, yes. So amazingly, just like there, here's the Euler-Lagrange equation. It turns out, since all the pinning is at the origin, you can eliminate the degrees of freedom away from the origin and reduce everything to just a single degree of freedom that's sitting at the origin. That's a displacement of the origin. Amazingly, what you get is a problem that's known in applied mathematics as the Sine-Hilbert problem. Is just a Sine-Gordon model, one-dimensional Sine-Gordon model, but with the kernel that's not elastic, but it's a long-range kernel that I indicated here. And here's the tilting. Here's the corresponding Euler-Lagrange equation, which is the Sine-Hilbert equation. This is a Sine-Hilbert transform of the elasticity. Amazingly, although I went and solved this problem to the extent that I needed myself, it turns out that there are nonlinear solutions to this equation, Salton solutions, and here's the basic one that goes back to Peierls and Nabarro in the 40s, and then was actually fully explored as an integrable model by Ablowitz using inverse scattering methods in the 80s, in the mid 80s. So what does this have to do with the tilting transition? Well, so when you apply this tilt, here's how you can study the ground state in the presence of this tilt, and indeed what you get is a commensurate incommensurate tilting transition. So there's a phase in which a vortex line likes to sit in a columnar defect, and there's a phase that's at small tilting, small transverse field. If the transverse field is large, the tilting is large, then they tilt away from columnar defects. But in between, the process of going from here to the tilted state is by proliferation of solitons, precisely the solitons discovered by Peierls and Nabarro. And all that happens is as you apply bigger and bigger field, transverse field, you get more and more of these solitons. Eventually, those solitons overlap. So it's like the Sine-Hilbert analog of the commensurate incommensurate Sine-Gordon transition that you're familiar with now in this transverse direction. And here's the picture, and you can study this, and it looks like actually without tilting, it looks like the Kane-Fisher impurity problem. Oops. Sorry, it looks like a Kane-Fisher impurity problem. You get Friedel oscillations, or all kinds of interesting stuff. But then beyond a critical field, you develop a single. So this picture is a 1D picture where I've eliminated degrees of freedom away from the columnar defect. That's this picture. So if you wish, it's the Kane-Fisher analog. It's the analog of Kane-Fisher, or really it's it's vortex analog, where I integrated the modes away from the impurity. But I could reconstruct those modes now because I know the whole distortion, because the bulk modes are related to the surface modes on the columnar defect. If you reconstruct it, it looks like this. So this is sort of the Meissner phase to those, to the tilting solitons of Peierls and Nabarro. And when you exceed the HC1 in the transverse direction, you develop a single soliton. But of course, in that soliton is not just a single soliton, it propagates into the bulk. It decays with an amplitude, but nevertheless, it distorts things very far away out to the length scale of the system size inside this bubble. So that's kind of a cool problem. As you push further, more solitons develop, and eventually they begin to overlap, and now you have a smooth tilting, except right near the columnar defect. So there's this phase diagram that I developed. There's a commensurate phase, tilting phase, incommensurate tilting phase, and then the fully tilted phase. So you go from here, that's like the Meissner phase for tilting. That's the Bose glass, analog of Bose glass for one column. Then solitons enter in this really correlated way. And then finally they overlap, so you get to this thing. Okay, so that's, again, still a little bit of a background, but I think that's still an interesting story. But now the question I really wanted to ask is what happens if I tilt by a lot? So suppose I tilt rather than some angle that I was exploring just now, I tilt by pi/2, so vortices are now running perpendicular to columnar defect. And the question is there a new phase hiding there somewhere, or is this just some vortex liquid? And even a little bit of qualitative thought tells you that there's actually, this leads to a new phase of matter, of vortex matter. Why? Well, here's the picture of it. So here's my three-dimensional picture. Here's the columnar defect. So I'll call that z-axis of columnar defect. Magnetic field now is applied perpendicular to it along the y-axis. And then there's, of course, the x-axis. So you sort of have planes. You have flux lines that are running like this in sheets. And what do they really see? What they see as cross-sections of, cross-sections of these columnar defects of point disorder for the distortions in the x direction. And these columns, let's assume they're z independent. So there's no randomness in the z direction. So what kind of phase do you get? And that's the phase I call Smectic vortex glass. So let me now describe it in detail. So if I can get through this slide, then you will know everything about Smectic vortex glass and the rest details about derivation of it. So first observation is because there's disorder now is independent of z, that means there's nothing that forbids, and in fact, at low temperatures, you will always have uz, the distortions in the z direction are 0. And that's because columns are independent, translation invariant in the z direction. So therefore, vortices will form periodic sheets in the xy, along the z direction. So there's actually a crystalline order in the z direction. That's why I call it a smectic. And one can probe that order by calculating structure function. So along the scattering along the QZ, along the columns, you get true Bragg peaks. Okay, because at low temperatures, because there's nothing, it's like a crystal it's a one-dimensional crystal in the sense of this is periodic. On the other hand, if you look transversely to columns, then the vortices just see these point disorder coming out of the page. And they're randomly pinned like this. So then it turns out, as I will describe if I get to it, that it's power law rough, and you get, in fact, at least within the Bragg glass picture, you're getting Bragg glass like logarithmic distortions with universal amplitude, A sub d. And correspondingly, if one looks at the structure function in the perpendicular direction, you get power law structure function rather than delta functions. So it's delta function in this direction, but it's power law function with a universal exponent in the direction transfers to the columnar defect. So this is power law, but it's periodic in this direction, in the z direction. Any questions about that structure? Okay, well, let me tell you some more properties of it, which kind of just follow even qualitatively if you just think about this. So this one does not quite, but it's not, it makes sense. Elasticity actually is described by a divergent shear modulus. If you try to take these sheets and shear them in the ZX plane by taking the state and shearing it like this, by trying to tear away vortices from columnar defects, then you get a divergent, you get a response that suppresses that tilt. And in fact, the state is described by anomalous elasticity, where you have du dz, the distortion in the x direction, gradients of along z of ux actually have a non-analytic behavior. There's no square here, it's actually absolute value. So there's really a breakdown of elasticity, and this was what I call shear Meissner effect for the Smectic vortex glass, as to be contrasted in analogy with the transverse Meissner effect of the Bose glass, when vortices run along columnar defects. Finally, the most striking thing is the transport. So think about what happens in, well, so let me just first state it. There's a so imagine I run current in the z direction along the columnar defects. When I do that, that creates a Magnus force perpendicular to columns. So there's a force on vortices that pushes them in this direction across the columns. Because they're pinned by the cross sections of the columns, they cannot move. And therefore you have a vanishing resistivity. So the point is, for current along this direction, there's no voltage. On the other hand, if you try to flow current perpendicular to this direction, then there's a force of vortices along columns. So but since there's no pinning along the columns, the whole structure can just slide up, and there's a flux flow resistivity for current along the x direction. So this results in the divergent anisotropy in the resistivity. And so here's a schematically indicated that below TC, rho ZZ or RZZ is, goes to 0, while the rho XX is finite at any finite temperature. And so here's the answer to my question marks that I posed in the opening. Here's the Nelson and Vickers Bose glass. Here's the vortex liquid in which you can melt to. But here's the intermediate phase that I suggest is a Smectic vortex glass phase, whose properties I just described. And all that tilting transition happens here in an intermediate values. And I sort of suppressed it here. So this is everything that you need to know about the actual state, or the claims about the state. The rest, in the remaining 15 minutes, I can quite easily tell you about how I got these results. But maybe this is a good point to pause, because the rest is shifting gears and actually discussing how you study this kind of a phase.
Yeah, so actually I probably missed something, but when you were talking about the tilting, you had an HC1 and HC2, right?
Right, it's sort of hidden in here. So it's a great question. So like I said, I suppressed it.
Okay.
There's an HC1 here, there's an HC2 here, and here's some complicated intermediate tilting phase of solitons. Now, this is, I don't really understand this in detail, because I've only studied one columnar defect and many vortices in 1+1 dimension. So I don't really have a detailed theory. There was a really nice work by Terry Juan, Nelson, and Vinocourt and then others as following it, that studied what happens in this tilting transition. But more generally, and sort of using scaling arguments, but there's no detailed theory in 3 dimensions and multiple columnar defects that I have in this region. But so I sort of, for simplicity, I suppressed it.
But could this region which you have suppressed, could it be also some kind of a glass, or?
Yeah, I mean, well, yeah, I think it is a glass, but I don't really understand it. So let me I don't understand. I don't understand its properties. I'm quite confident about large tilting, but I'm less confident what happens here in this more complicated region.
Okay. Okay. So when you say it's a Smectic vortex class, you are like reasonably above HC2.
Exactly. I'm really looking even worse. To be totally honest, I'm looking like we're at infinity here.
Okay. Okay.
But experimentalists plot really theta here. So I'm at pi over 2, and that's, if you look at that, that's what so I'm looking at pi over 2 strictly. All the calculations are done for pi over 2. Everything else is hand wavy.
Mhm.
And there's actually a rich story that I'm not gonna talk about today. Of what I do have some understanding what happens as you kind of reduce the away from this pi over 2 limit.
So experimentally, do the boundary conditions like matter a lot? Because when you're doing this tilting, somehow like there's this
Yeah,
shift.
there's all kinds of questions about barriers at the boundary of the sample that this definitely doesn't take into account. You're right.
Mm-hmm.
So this is a model.
Okay. Okay. Yeah. Thanks.
Other questions?
Yeah, the silly question. I'm a little confused. So, AC2, I thought is when vortices start entering the material, right?
No. This is HC2 perp.
Perp. Oh, okay. That's sorry about that.
Yeah, this is all perp.
This is all perp.
I have my
Okay.
vortex matter. That's unquestionable. That's because I'm sitting at some overall H. And now
Yeah,
I'm trying
and
to tilt it.
Right, and it's smaller, and that's the H is smaller than the AC2 of the
Yeah,
of the
exactly.
superconductor.
Yes, that's right. It's all much smaller than HC2.
Yeah.
And is there a concern about probably not. So in type 1 superconductors, when there's this mixed state of some region wants to become normal.
Right.
there
So
a
there's a
concern about that
possibility
here?
of getting, you're right. There's a possibility of getting, well,
I mean, this is strongly type 2 superconductor.
yeah,
so you
I'm
won't
considering
normally
it strongly
expect
type
that.
2 limit.
It's not normal to get any mixed state. So
Yeah.
it's just this unusual state which can propagate in one direction. But it's anisotropic resistivity. So it's suggestive of it feels a little bit like a mixed state, but it's not mixed in space. It's just mixed in
Yeah.
dimensionality.
Yeah, it's not really mixed. I think it's a fully bulk state. It's
Yeah.
not just coexistence of anything.
So there's no instability, I guess, to phase separation. I should ask.
No, I mean, if I'm strictly in type 2 limit, deep in the type 2 limit, there's no instability. The only thing I'm saying is very simple. I'm saying there's, columns distort things in this direction, but they do nothing in the Z along their direction.
Right.
And therefore you
Right.
get periodic order here. Of course, you can melt that periodic order with temperature and go to a liquid state. That's just this. But you also want to understand the state first. So let me try to show you the model
Yeah,
that
I can
describes this.
Mhm.
So it's very simple. So you start out with some elasticity. It's biaxial elasticity because there are really 3 axes here. This one, and this one. And they're distinct axes. And then you have a pinning potential. Unlike single pin, this potential is a random potential that acts on the vortex density n, and it acts everywhere. It turns out you can rewrite this theory, this model, in terms of some effective elasticity characterized by a kernel gamma. And then there's a random field-like term. If you think of this as an XY model, there's a random field-like term that couples to the UX, but not UZ degree of freedom. And that's easy to understand. There's no point of distorting in the Z direction because columns, there's no pinning in the Z direction. So UZ is really, roughly speaking, 0, at least at 0 temperature. Okay. So the only variable we're going to focus on, at least for disorder case, if we focus on disorder, is UX, which I'll often just call U. But anyway, this density is just the standard density that you've seen If you do Lagrange liquids, that's what that density is. It has a long wavelength component and it has a periodic component. So this is the pinning, and this is kind of the long wavelength part. Just like in Lagrange liquids, when you describe Lagrange liquids, there's a long scale part of the density and there's a 2kF part of the density. And disorder is correlated, is uncorrelated. So in space, it's uncorrelated. And then there's a variance, and that variance, one cool important part about this variance is it's a function, and that function has to be periodic in U. And the reason it's periodic is because you can take the whole vortex lattice and move it over by one lattice, by one set of vortices. You know, but you basically this arises, this periodicity arises because vortices are identical. And so there's a really an identity, but it's probably simplest conceptual to think of it. If this was a crystal, if you move all vortices by a lattice constant, your pinning has to return to the original pinning. Just because it doesn't make sense to move vortices energetically, it doesn't pay to move vortices more than a lattice constant in a vortex lattice. But the amazing thing, this persists beyond even when you destroy the vortex state. Anyway, so let me just move on. You can now ask, how do you melt this thing? That's the simplest thing you could do. So the way you melt it is, you know, or the way to get a criteria of how it melts, you simply crank up the temperature until this criterion is satisfied. And that gives you, this criteria is temperature dependent. So this gives you a melting temperature, just for the record. And that just tells you about the smelting. But the more interesting part is the disorder part. So as I already mentioned, the first thing one does, one looks at, focuses on zero temperature for now, and one studies correlations or variance, fluctuations or distortions of vortices perpendicular to columnar defects. This is the UX. So now I'm looking from the top on this picture, like this. And what one discovers is indeed there's a finite Larkin length scale, which means it's completely disordered in this direction beyond a Larkin length scale, just like what I discussed for the vortex class, except in this new context. So now one can just say, okay, I'm happy with that statement, but that's an incomplete theory. One wants to know what happens beyond this Larkin length scale. That's sort of going into nonlinear theory of pinning. And there's a very beautiful study of this, and really goes back to Daniel Fisher, as many things in the subject, of studying pinned elastic medium in random potential or random field XY models, where there's an Imry wire length or a Larkin length. And one can study this, and this goes back actually to 1985. And so to go beyond this Larkin scale, where the lattice is beyond it, lattice is distorted beyond recognition, but nevertheless, one doesn't know what happens beyond that length scale, like what kind of a state does one get. To understand that state beyond Larkin scale, one needs to do what's called a functional RG for this whole function R of U minus U prime, namely the correlator of the random potential. Okay, you can no longer describe it by a constant, which you can on short scales, but at long scales, you really need to keep this whole function together. That's because you have one way to say it is you have infinite number of relevant random operators that appear. And this was first understood by and pointed out to the community by Daniel Fisher. So if one does this, and by now that's a fairly standard procedure, so I'm not going to dwell on it, I'll just show you what the results are. So one way to do it, there are many ways, or a number of ways, is to replicate this Hamiltonian. So that means you integrate out disorder, but you introduce replicas. So now we're z to the n, and then you integrate disorder out. So you get z to the n averaged over disorder, and your replicated Hamiltonian, and you call that your replicated Hamiltonian. The replicated Hamiltonian has some elasticity part that you've already seen, plus it has this variance of disorder that appears. We take disorder to be Gaussian, but the variance is nonlinear function that's periodic in its argument. So what comes down to in this study is to understand how this variance, this function R of U, flows under coarse graining. And that's what led to those results that I mentioned for the vortex glass state, or for the Bragg glass state that Daniel Fisher and Gianmarco Ledusal and others have studied. Here is just in this new context. The other ingredient is actually this elasticity that does not get renormalized except for one particular component of it, which has this shear modulus mu zx for distortion of the crest of this vortex lattice for non-uniform distortions of or shearing of the vortex lattice in the zx plane. The upshot of this RG analysis is that you get an RG flow equation below five dimensions. Disorder is relevant rather than below 4 dimensions. So that's because the disorder is correlated here. So here it's much more relevant by unit of dimension. So below 5 dimensions, you can do an RG epsilon expansion for the spinning potential. And what you get is its effect is summarized by this flow equation. This flow equation is a partial differential equation in the RG flow, but also it's also a differential equation in the argument U of the random variance of disorder. So this is how infinite number of relevant operators appear. If you Fourier transform this or do a Fourier series on this periodic function, you'll get infinite number of Fourier coefficients. They're all equally relevant. They're all equally relevant because the temperature is irrelevant in below 5 dimensions, or above, I should say, above 2 plus epsilon dimensions. And because temperature vanishes, goes to 0, it's a dangerously irrelevant variable. All the harmonics of this random potential are actually equally relevant. And so one has to study a whole function, and hence functional RG. And it's controlled by epsilon expansion around 5 dimensions. So what's the upshot of the answer, of this procedure? And again, this goes back to Fisher and Gianmarco Ledusal and many others in many other contexts. It's controlled by a 0 temperature fixed point, and the fixed point function of this PDE is actually this, is just a parabola which is periodically extended, because it has to be a periodic function. So the way you should think of this is it starts out being a cosine potential or some kind of a periodic potential that's smooth, but the effective disorder creates cusps at when you periodically extend this parabola. So in other words, instead of being a cosine, it's actually parabolas that have slope discontinuity at 0 and at A and at 2A, etc. This is what this function is. Here I only draw it's one period. I only draw this. Okay? So I draw a single parabola. Now, so that's the flow of the random potential, but it turns out that the random potential, these cusps, are actually rounded by finite temperature. So if the temperature is finite, and even though it's flowing to 0, it's dangerously irrelevant, so because it creates cusps. It becomes sharper and sharper as the temperature flows to 0. And that is what responsible for, well, for example, so what one can ask is, what is the correction for this shear modulus in the presence of this random potential? And what one discovers is that the correction is proportional to the second derivative of this random potential. But since the first derivative jumps, the second derivative is actually infinite. So this thing is actually has an infinite correction. It's infinitely receives, this guy is negative at the fixed point. So this guy flows to infinity, to positive infinity. And so the question is, what is the interpretation of this? And this was actually understood back in '93. Leon Polenza and I we were still graduate students at Harvard, and we had, we were studying this problem. Then Leon actually solved this problem, and it was published in the Europhysics letter in '93. And the upshot of this, he wasn't studying in this problem, he was studying in the Bose glass case, but it turns out you can take advantage of those results and understand how the sharpening this potential, what is the consequence of that for the shear modulus. And the upshot is that you generate a term like this, which is the absolute value of dux dz. And so as a result, that is really a proof, or this absolute value is really a way to understand where the shear modular Meissner effect comes about. So that there's a vanishing response to shear because of, if you apply a shear stress in this ZX plane, the system is not going to respond. So there's a shear, I call it a shear Meissner effect, as compared to the shear transverse Meissner effect. So yeah, so this is sort of a loaded slide, but you don't need to understand its technical content except its claims. So let me just move on then. There's one last sort of nail in the coffin that is always plagues this subject, namely the question of dislocations, or more generally topological defect. You see, the problem is already quite non-trivial, even if you assume Bragg glass, and ignore dislocations or ignore topological defects, because you have already very non-trivial nonlinear competition that led to these results between elasticity and pinning. Okay, so already this problem presupposes at this level that there are no topological defects, no dislocation. But now I have to fix up and I have to make some arguments about including topological defects, namely dislocations. And that's an infinitely, you've just infinitely made the problem potentially infinitely harder, because now you have disorder, elasticity, and topological defects, singularities in the distortion field. So that's challenging. And that's what I said for ordinary vortex glasses. We believe in 3 dimensions from simulations in real space RG by Daniel Fisher that it is stable. There's a Bragg glass state. But here, actually, the situation is much simpler. There's a set of ingredients that I list here, but most important of which is the columns are Z independent. Disorder is completely Z independent. And that tells you, in fact, one can use that to argue that, in fact, there are no dislocations in either the XY plane or in the XZ plane. And so indeed, dislocations do not proliferate. And indeed, I argue that this picture is in fact stable to proliferation of dislocation. So I believe this is the correct picture, even if you allow for the possibility of dislocation. For weak enough disorder, they do not proliferate. So with this, let me just finish with a summary. So I gave you 30 plus years of overview of vortex physics in type 2 superconductors in the presence of thermal fluctuations and pinning, all kinds of pinning, point pinning and columnar pinning. And then I moved on to talk about my recent work that actually dates back more than 20 years, maybe 25 years back, when we were looking at this. I predicted a Smectic vortex glass phase that's illustrated here. Here's the phase diagram as a function of a transverse field. It appears here. It has an interesting structure that's very anisotropic that you can detect in scattering, neutron scattering, for example. It has a divergent resistive anisotropy that's schematically illustrated here. It has a divergent elastic response, which I call a shear Meissner effect. And I believe this state is, for weak disorders, a true Bragg glass state. So with that, let me quit, and thank you for your attention.
So you were drawing these pictures with the field perpendicular to the columnar defects, but you mean that it's actually stable to tilting, correct?
Yeah, so it's stable to, sorry, are you talking about this last effect? Or are you talking about
the picture on the slide, the vortex the field and vortex lines are running perpendicular to the defect.
Okay, this picture, we're in here.
Yeah, but with H perp.
So H perp, strictly speaking, the ratio of H perp to H parallel is infinite. We're at pi over 2 tilting.
I see. So this is you did not mean to put it into the phase diagram with where you slowly tilt the field.
Right. Well, that's what I said before in response to Arpit. There's a region here that's complicated. How you go from large tilting to small to no tilting, and that's like an intermediate state of tilting that has those solitons in there. Although I don't have a theory for it. Now, pi over 2 is somewhere over here at infinity. Now the question is, how far down does this survive?
Mhm.
And I believe the symmetry of it, and there's some rich things that happen that I have studied, but I'm not prepared to talk about in public, that it does survive. It doesn't just happen at pi over 2.
So you do mean that even though all the pictures, the field was perpendicular to the defects, you do mean that it will then be stable.
Exactly. I do mean that. And let me just try to give you some picture of what it's kind of a cool thing that I was really intrigued about, but never made completely work. So think about if you're tilted at some angle, but that just say it's a large angle.
Mhm.
What's nice is columnar defects still look like point impurities in this plane.
Mhm.
But what they're pinning is they're not pinning just one point, one intersection point. They're pinning this whole region. So what I believe happens is, as a function of angle, you actually increase the effective point disorder that the flux line, the vortices see.
Mhm.
Because they're pinned,
Mhm.
they're attached to this column, with over this finite length scale. So in fact, this allows you to tune the strength of the effective point disorder of the cross sections, which are now little stubby little columns of finite length of this length.
Mhm.
And so there's a whole story there that, like I said, I have not fully developed. But so let me just leave it with these
Okay,
comments.
thank you.
Yeah, so is there some interesting effect if you have these perpendicular fields along two directions instead of, so that the tilting
But it's uniaxial around columns, so I don't see what you mean.
okay,
Like,
yeah.
It's just completely isotropic around the column axis.
Yeah, I was wondering whether you could join these columns in some unique ways. Right now, it seems very, they were just going up and joining the next column and then straight, something like that. But maybe, yeah, maybe you're right. There's some symmetry because of which it doesn't matter.
Yeah, there's complete, at least within this model, it's complete isotropy in the plane, in the XY plane perpendicular to the columns.
Right. Yeah. Yeah. So one thing which I probably didn't appreciate that well is this absence of the dislocations that you mentioned.
Yes.
What was your argument again for this?
Well,
in the
okay,
case
so
of Smectic
imagine you look from this direction right here, from here.
Yeah.
So think of it, your eye is looking in this direction. So there's a UX and UZ. So the first observation is, so that means there are dislocations, like if these are flux lines coming out of you from the y-axis. So what I'm saying is, so what a dislocation is an extra column like this. So there has to be a non-trivial circle, non-trivial cycle around in the XZ plane, looking from here in this plane. But since things are Z independent, this non-trivial, this curl cannot be non-trivial.
Mhm.
So there's no Burgers vector in this direction. But then you might ask, well, what about, look at one of these planes, you're in the XY plane, can there be a dislocation there? Well, that's ignore UZ. UZ is 0. So now let's look at this picture in the XY plane. And that just comes from divergence of B equals 0. If flux lines cannot go, if vortices cannot go from plane to plane, there'll never be, when they go from plane to plane, you can create a little extra line like this. That's just a vortex line hop from one plane to the next plane. But if they don't hop between, there's no UZ, UZ is 0, then this is the picture you have, which is the Carty-Ostlund, Matthew Fisher glass in 1+1 dimension. That's what one of these planes is. But then just the continuity, divergence of B equal to 0 just says these lines cannot end.
I see. Okay.
And that's just this statement exactly.
Mhm. Mhm.
You see, Bx is this and By is this. And if you take a divergence of it being 0, that's the same thing as this being 0. But that's just exactly the XY curl of a gradient.
Okay.
So that must be 0 by just no monopoles.
Mhm. Mhm.
So the arguments here, I believe, are far stronger and much simpler than in the vortex glass state, for point disorder.
I see. So the terminology Bragg glass is used when you don't have dislocations. Is that right?
Yeah, it's just,
Okay.
this is what Gianmarco Ladosal called it. They invented it.
Mhm.
Before them, people were always doing the calculations like they do for Bragg glass, except it was, always with an apology that, oh, this only works up to dislocation on binding scale. They made it this conjecture and made strong arguments for it. But I believe, there's simulations and, real space RG that's put some meat and some calculation on this question. But, Bragg glass is really synonymous to a topological state in which there are no topological defects. It's only elastically distorted. And again, you can think of this as a disorder-driven analog of the Castells-Talos phase, where you have distortions, but those distortions have no vortices, namely no topological defects in the power law phase.
I see. Thanks. That's very helpful. Yeah. So
I think I have to run,
Yeah.
unfortunately.
Right.
I have an appointment with a COVID testing site.
Okay.
We're traveling finally, and so I need a COVID test.
I see. Yeah.
In 15
So
minutes.
right. So no.
I appreciate all the questions and
Thank you.
Yeah. Thanks
Yeah.
a lot for a very nice talk and tutorial. Yeah, this was very helpful.
and if you guys have questions, feel free to email me anytime, of course.
Okay. Great.
Okay, bye-bye.
Bye. Thank you.
Thank you.